Let us start the definition of subgroups today. Um, Subgroup. Let G star be a group. A subset H of G is a subgroup if H is a group by itself under the same induced binary operation in G. So let us take some examples here. We know that Z plus, this is the first group we discussed, is a group, is a countably infinite abelian group. So if you take NC, NC is defined as M in Z is a subgroup of Z plus. Because NC itself is a group. It has got the identity 0. It is closed under addition. It is definitely associative because it is coming from the Z. And for every element here has an inverse. What we have to note here is that this binary operation is same from the parent, the group and the subgroup. This has to be same. This binary operation on subgroup is induced from the group. It is not that just NC is a subset of this. Take another example. You know, R plus is a group under addition. But we know that Q star, this is actually the set of all rational numbers, set of all non-zero rational numbers. We created a group with a set of all rational numbers. Actually, that is Q star dot is a group under multiplication. But as a set, Q star is a subset of R. But Q star multiplication, Q star dot is not a subgroup of R plus. Because the binary operation is different. That is very important. It is not just the subset. The subgroup has to get the binary operation from the group. It is same. Now, you are going to derive a necessary and sufficient condition for a subset to be a subgroup of a group. So let G be a group and H is a subset of G. Then H is a subgroup of G. Later on, we will not use the whole notation. We will just say H is a subgroup of G. Okay. So just want to make sure that here also I'm going to mention, because I just want to make sure that the binary operation on the subgroup is same as the binary operation on the group. If and only if this is a subgroup of this, if and only if there are three conditions. H is closed under the group operation. Second one is H has the identity of G. Third one is for every A in H, A inverse also belongs to H. If these three conditions are satisfied, then H is a subgroup. It is the proof is very straightforward. First, we assume that H is a subgroup of G, and that definitely implies 1, 2, and 3 are satisfied, because this itself is a group. So that implies 1, 2, and 3 are satisfied. But we want to find out if this is true, then H is a subgroup. In order to prove that H is a subgroup, we need to prove that H itself is a group. So what are the conditions on H? The only condition which is not shown here is associativity. See, H is a group if 1, 2, and 3 are satisfied if the binary operation in H is associative. That is the only thing which is not proved here. But A comma B comma C belongs to H implies A comma B comma C are in G, because H is a subset of G. And since these are in group G, A star B star C is equal to A star B star C. So that implies H is a group under star, which implies H star is a subgroup of G star. And by the way, if H is a subgroup of G, we'll write it as H less than or equal to G. This means that H is a subgroup of G. Let us prove a very simple theorem. Let G star be a group and A belongs to G. Then the set H is equal to A to the power of n, where n belongs to Z, is a subgroup of G. Let's do an example here. Let's say G is equal to Z. So Z is equal to 0, 1, 2, 3, minus 2, minus 1, minus 2, etc. So let us take n is equal to 3. So what does this mean? So H is equal to 3Z. That is 3 to the power of n, n belongs to C. And that is actually equal to 0, 3, 6, etc. minus 3, minus 6. And that's what we are going to prove here. So what we have to note here is that A to the power of n means A times A times A dash dash A times n times. And we are going to assume that A to the power of 0 is equal to E. And that is because using this notation, A to the power of minus n or A to the power of minus 1 is actually the additive, or I don't want to say additive. A to the power of minus 1 is the inverse of A. If it is addition, we normally write it as minus A. If it is a multiplication, we normally write it as, or in general, if it is a star is a binary operation, we normally write it as minus 1. So why is this notation holds good? Because A times A to the A inverse is equal to E, or A plus minus A is equal to 0 or E. Both are identical. The only thing is the difference in notations. So when you have the definition of A to the power of n is equal to A times dash dash A, n times. So here this will be A times 1 plus minus 1, and that is A to the power of 0, and that is E. And that is why we are saying A to the power of 0 is equal to 0. So if you want to prove that H is a subgroup of G, we need to prove three things. H is closed, then H contains E, and for every A in H, A inverse belongs to H. So H is closed means let B comma C belongs to H. That implies B is equal to A to the power of I and C is equal to B to the power of A to the power of J for some integers I and J. Like it can be anything, any integers. So that means C is equal to A to the power of I times A to the power of J, and that is equal to A to the power of I plus J, and that belongs to H because I plus J is an integer. So it is closed. Definitely it contains E because H contains E because A to the power of 0 is equal to E and that belongs to H. And last one is also true. For every A in H, A inverse also belongs to H because minus 1 belongs to C. C belongs, if n belongs to C, then A to the power of n belongs to H. So that implies H is a subgroup of G, or H is subgroup of G. So that means every element of H is some power of A. Meaning, in this case, H is generated by A. Or we'll say that H is a cyclic subgroup of G generated by A. And we'll denote H is equal to A. So here in 3C is a subgroup of, cyclic subgroup of Z and is generated by 2. Now, if there existed A belongs to G, the whole G, such that G is equal to A, is generated by A, then the group G is cyclic. For example, Z is a cyclic group because Z is equal to 1. Now another thing we want to note here is there may be multiple generators. Here one of the generator of 3Z is 3, but there is another generator here and that is minus 3. Like that here the another generator is minus 1. So the generator of a cyclic group is not unique. The generator of a cyclic group need not be unique. There may be more than one generator. Please verify this. I'm not going to do the verification here, but please verify that. Now let us see some finite examples here. C6, 0, 1, 2, 3, 4, 5. And when I say C6, I assume that the binary operation is addition modulo 6. C6 is cyclic because C6 can be written as 1. Why? Because 1 is equal to 1, 1 plus 1 is equal to 2, 1 plus 1 plus 1 is equal to 3, 1 plus 1 plus 1 plus 1 is equal to 4, 1 plus 1 plus 1 plus 1 is equal to 5, 1 plus 1 plus 1 plus 1 plus 6 times is equal to 0. So this is actually 1 to the power of 1, 1 to the power of 2, 3, 4, 5, and this is 6. So we have the whole 1, 0, 1, 2, 3, 4, 5 in here. So this is a cyclic group. Now we'll take another element from here. So how do you find out the subgroup generated by 2 is equal to 0, 2, 4. And generated by 3 is 0. Well, this is actually, you are considering this as a subgroup of C6. Now we'll take another example here. A group with 4 elements. There are 2 different groups here. I'm going to use the word isomorphism later because we are going to study the homomorphism of groups in detail. So I'm not going to talk about isomorphism here, but I just want to say that there are 2 different groups with 4 elements. Meaning, if you say that the number of elements in a group are same, that does not mean that they are same group. They are totally different group. The way we are going to show this one is using the multiplication or operation table. So we'll see there are 2 ways of expressing this multiplication table here. In general, 4 elements we can write it as E, A, B, C. We don't know what they are. So E, A, B, C. And we are going to define the operation of these elements. Like that here also, E, A, B, C, E, A, B, C. When you fill up this table, this line is exactly the same as this. Like that here also. Now, we can write this, another one option is, this is B, C, E. Then C, E, A, and this is E, A, B. This is actually same as C4, that is 0, 1, 2, 3. This is 0, this is 1, this is 2, and this is 3. 0, 1, 2, 3. So 1 plus 1, 2, and that is B. 1 plus 2 is 3, and that is C. So that is how it is filled up here. So this is actually same as this. Only thing is we are calling 0 as E, 1 as A, 2 as B, and 3 as C. So these two groups are exactly same. If you fill this group, but there is another group sitting here. That is A square is AE, AB is C, AC is B. Both are commutative group, but there is a difference here. BA is equal to C, BB is equal to E, BC is equal to A. CA is B, CB is A, and CC is E. See, the identity is coming like this here, whereas the identity here is coming different ways. The reason why I brought up these two different groups is because the subgroups generated by elements are different in both places. Okay, this is actually called clean 4 group. Clean 4 group. And this is our normal C4. These two are not same because corresponding, if you take the corresponding elements, when you multiply, you won't get the same result. I'm not going to compare right now. There is a way of comparing two groups, and they are called homomorphisms and isomorphisms. We'll do it later. I'm not going to go very rigorously on that right now. All I want to show here is, let us take in Z4. In Z4, let us compute A. A means here 1. A is actually here, it's Z4. Because A is what? A is 1, right? 1 means if one can generate the whole Z4. And is B is what? This also subgroup. B is 0, 2. In Z4. C is equal to again the whole of thing, Z4. Okay? And if you take the E, it is the subgroup just E. This is actually, we'll say E and B. This is just E. So these are the 4 different subgroups of Z4. Whereas here in clean 4, for group, let us compute each and everything. A is equal to EA and B is equal to EB and C is equal to EC and E is equal to just E. So the subgroups generated by these elements are different. Another thing which we can show here is clean 4 is not cyclic, whereas C4 is cyclic. Because C4 is generated by either A or C, that is 1 or 3. Z4 is generated by either 1 or 3. There are multiple generators here. Here none of the elements can generate this. I want to give you another example of a cyclic group from geometry. This group you have already seen earlier. Un is equal to complex numbers such that the power of n is equal to 1. These are actually group of all nth root of unity. In other words, in a plane, they are the points on a unit circle. There are n points here. N points here. So these are the points in UN. Okay. So if zeta is equal to cos 2 pi by n plus I sine 2 pi by n, that is the first point here, cos 2 pi by n plus I sine 2 pi by n. Then un is generated by zeta, meaning there are n points here. So second point will be c square, c cube, then z to the power of n. See, when you multiply zeta times zeta, this will become cos 2 pi by n times 2 plus I sin 2 pi by n times 2. So this is actually generated by zeta. So it's a cyclic group. Now the question is, does this finite group have another generator? One generator is always like this. There are the generators of un are cos 2 pi by n times r plus I sine 2 pi by n r, where 1 less than or equal to r less than n, and r is prime to n. Not all the numbers, but they should be prime to n. For example, if you take U6, one generator is, the first generator is, or zeta is equal to cos 2 pi by 6 plus I sine 2 pi by 6. And that is this point, first point. Other generator is z to the power of 5, and that is cos 2 pi by 6 times 5 plus I sine 2 pi by 6 times 5. See, the elements in U6, once you find the generator, elements from U6 is equal to zeta square, zeta to the power of zeta cube, zeta 5 or 4, 5. And the 6 will be the identity. The 6 will be the identity, or we can say C6. This is our identity. 1, 2, 3, 4, 5, 6. And this is the generator. Now, let us assume that this is, we'll write it as E. So, the binary operation in this is actually multiplication. So, if U6 is a generator, U6 is generated by zeta, then it is also generated by zeta 5. Because zeta is, 5 is prime to 6. You can generate the whole numbers using 5. We'll do an example using the group of n by n matrices with real entries. So GLN of R be the group of n by n matrices with real entries under matrix multiplication. So my question is, if A is equal to 1, 1, 0, 1, find the cyclic subgroup generated by A. This is definitely a cyclic subgroup generated by A. So how do you prove? How do you find? We need to find out A square first. See what happens. 1, 1, 0, 1 times 1, 1, 0, 1 equals this is going to be 1, 1. So this is 1. And this will be, see, this will be this and this. So this will be 2. And this will be 0. And this will be 1. So if you find a cube, that is actually going to be 1, 2, 0, 1 times 1, 1, 0, 1. And that is going to be 1, 3, 0, 1. So an is going to be 1 n 0. So this is how you find the elements of this subgroup. So the elements of the subgroup generated by A is equal to 1 n 0 1 n in